this lesson for college algebra in Unit 4, we're going to talk about graphing polynomial inequalities and rational inequalities. So we're going to talk about shading, very similar to when we shade using linear inequalities. We have to make sure that our equation is set equal to 0, meaning that it is in its related equation form to help us graph a little bit. So this first one, we have x squared minus 4x minus 5. This is what we call a quadratic inequality. We already see that it is greater than 0, and I'm just going to replace that greater than symbol with equal to for the purpose of solving so that we can find the x-intercepts. When I find the x-intercepts, I'm going to factor or use the quadratic formula or any other method that you know how to solve for the x-intercepts. When I factor, I'm finding two values which multiply to -5, but yet add to -4. And I see that -5 and +1 will work. So its factored form will be x minus 5 times x plus 1. Setting each piece equal to 0, we'll have x is equal to 5 and x is equal to -1. So our x-intercepts are 5 and -1. So we could actually plot them on a graph as we're working here. That's kind of split our area or our quadrants into 3 different areas. We have the 3 different areas of between -infinity and -1, between -1 and 5, and then 5 and infinity. We are wanting to determine whether we will have positive or negative results. And notice here we want greater than 0 results. So things that are greater than 0, just going to make a note that we want positive results only. So I have a table of values here. Our interval between -infinity, -1, -1 and 5, and 5 and infinity. So I'm going to use a test value, and I want to determine what is the sign. Is it positive or is it negative? When I substitute -2 into my function and evaluate, I end up with a positive result. So between -infinity and +1, we have a positive result. What happens between -1 and 5? I'm going to substitute in 0. And when I substitute in 0, I end up with a negative result. So we are negative in between this interval. And finally, the last interval between 5 and infinity, I chose 7. When I evaluated f of 7, I end up with a positive value. So between negative and infinity and -1, I'm going to shade here because this is where my graph is positive. When I hit -1 to +5, my graph becomes negative down here. And then we become positive again on this side. So we're going to shade over here as well. We then can say that our solution set then is from -infinity to -1, union, skipping over this middle portion from here to here because it's negative, from 5 to infinity, or x such that x has to be less than -1 or x has to be greater than 5. In example 2 here, notice it's not set to 0, so I want to make sure that we set this to 0 first before we start solving. I'm going to subtract x and subtract 3 and bring them over, which provides us with x squared plus 2x minus 8. And then we're going to simplify by factoring. When I factor, I can find two values that multiply to -8 and add to 2. So 4 times -2 will give us a proper solution, x plus 4 and x minus 2. When I solve each one, I'll have x is equal to -4 and x is equal to 2. So our x-intercepts, are from -infinity to 0 and then from 2 to infinity. Now we need to determine where we're going to shade. We want values that are less than or equal to 0. So my points here, we need to know what's happening in between here. So my intervals are from negative infinity, well, yeah, we'll do negative infinity, to negative 4, between negative 4 and 2, and between 2 and infinity. If I were to evaluate such at f of negative 5 as an example, if I did f of negative 5, I would end up with a positive result. If I did f of, let's say, 1 would be in that interval, I would end up with a negative result. And if I evaluate, let's say, f of 3, I would also end up with a positive result. This tells me that I'll be positive on the left-hand side, and I'll be negative between these values, and then positive going forward. And I'm only interested in those values which are less than or equal to 0. Our solution set then is on the next page at the top. Our solution set then is from negative 4 to 2, inclusive because of the less than or equal to symbol, or x such that x has to be in between negative 4 and positive 2. Let's try another example here. Here we have x cubed minus x. We're looking for values of x that are greater than 0. So let's go ahead and factor this as best we can. I see that they both have x as a common factor. So when I factor out x, I have x squared minus 1. Here we have a difference of perfect squares. And when I factor the difference of perfect squares, I'll have x plus 1 and x minus 1. We have 3 solutions then. X is 0, x plus 1 is 0, and x minus 1 is 0, providing us with the values of x is 0, x is negative 1, or 1. Our x-intercepts then are 0, 0, negative 1, 0, and 1, 0. That means that we have 3 different places that we need to consider. We need to consider negative 1, we need to consider 0, and we need to consider positive 1. So in between which intervals that we have. Here we have 4 intervals. Again, we're looking for values that are greater, so we're only looking for positive values. So we know where we need to shade on the graph here. I have my intervals between negative infinity and negative 1, negative 1, 0, 0, 1, and between 1 and infinity. I'm going to choose negative 2, which is in between negative infinity and negative 1. I end up with a negative value. So on this side, I have a negative value. Between negative 1 and 0, I'll choose negative half. We end up with a positive value. So between negative 1 and 0, we are positive. Between 0 and 1, I'm going to select half, which ends up with a negative value when I substitute. So here is a negative value. And then between 1 and infinity, when I substitute in 2, I end up also with a positive value. So between here and here, I have a positive value. So when x is, the only values are between negative 1 and 0, we are positive. And between 1 and infinity, we are positive. Our solution set then is between negative 1 and 0, along with between 1 and infinity. So we also could write this as x such that x is between negative 1 and x has to be also greater than, between negative 1 and 0, and then x also has to be greater than 1 as well. Now we've got 3x to the fourth plus 10x is less than or equal to x cubed plus 11x cubed plus 4. We need to set this equal to 0. So we'll subtract 11x cubed and subtract 4 and bring to the left. That will provide us with 3x to the fourth plus minus 11x cubed plus 10x minus 4 is less than or equal to 0. So again, we're looking for values that are less than 0. So we're looking for negative values. We actually solved this equation in section 4.4, example 5. And the approximate solutions were given here, but we did have the exact solutions given below. The exact solutions were -1, 2 plus and 2 minus square root 2. We also had 2/3. And that means that we've got 1, 2, 3, 4, 5 different intervals with which we need to test. And down below, I actually have the graph listed with the different intervals. So let's give ourselves a test between grabbing these exact approximate values and then going ahead and testing some values. So between -infinity and -1, our option is -2. Of course, you could choose any value in that order, but all I care about is that it was a positive value. Between -1 and 2 minus the square root of 2 would be 0. And when I substitute 0 in, I end up with a negative. Between 2 minus square root 2 and 2/3, I chose 6/10. We have a positive value. Between 2/3 and 2 plus the square root of 2, I chose +1, ending up with a negative value when substituting. And finally, 2 plus square root 2 to infinity, I chose 4, which was a positive value. We're looking for negative values, so the only intervals where I ended up with a negative value were these two places. So between -1 and 2 minus square root 2, we are negative, as well as between 2/3, which is 0.667 on our graph here, and then 2 plus the square root of 2, this area, we are negative. So we've got ourselves the interval, inclusive because it was less than or equal to, between -1 and 2 minus square root 2, union, also inclusive, 2/3 to 2 plus square root 2. Or we can write it in set builder notation here, x such that x has to be in between those two values, or x such that x has to be in between 2/3 and 2 plus square roots of 2. Again, using decimals to help us graph so we can actually see things come together as we're building is essential. Now let's move on to rational inequalities. We still have to be careful for where x can't be because of our denominator, so keep that in mind. We're looking for values that are less than 0, but we also need to find critical values. First, our critical values are when our function is not defined. So I need to understand where my x cannot be defined. So x can't be 0 in our denominator. So x, we have to be careful when x is -6. That's a critical value. Also, the values for which when we solve for 0 are critical values. So first, the critical values is when it is not defined. And critical values is when we set it equal to 0. Those are the two pieces that we need to do. So as to set this equal to 0 and solve, I'll multiply each side by x plus 6, which then creates a common binomial which we can eliminate. I am now left with 3x equals 0, or when we divide by 3, 0. So I have two critical values. My critical values are at -6, the value with which would give me a 0 in my denominator, as well as 0 when I solve and set the equation equal to 0. I need to decide, again, we're looking for less than, so we're only caring about the negative values once we graph and what that might look like. And I think the graph's on the next page. When I substitute in my intervals -8 in for the first interval, I end up with the positive. When I substitute a value between -6 and 0, here I chose -2, which ends up with a negative, so we're negative in between here. And then between 0 and infinity, I substituted 3, which I ended up with a positive value. So the only interval with which I ended up with a negative is in the interval between -6 and 0, excluded because it's only a less than sign, or x such that x has to be between -6 and 0. So what would that graph look like? Here's our graph, and only in between -6 and 0, so this area here, -6 just happens to be an asymptote for us, so it won't actually be, which is why we use less than or equal to. So in between here, our graph is less than 0. Example 6, we have another rational inequality. We want to set it equal to 0, much like we've done before, so I'll subtract 1 from both sides. When I do that, we have our related equation. We need to find the critical values. We need to identify, again, where our graph will not have 0 in the denominator. So if I set 2x minus 4 equal to 0, x is 2 is a critical value. Our other critical value, and here's x is 2. Another critical value is when I set it equal to 0 and solve. So I'll add 1 to both sides, multiply both sides by 2x minus 4. So I can eliminate my common binomial here. I now have x plus 1 on the left, and when I distribute 1, we have 2x plus 4. I'm going to subtract x so that I have 1 is equal to x minus 4. Add 4, so x is 5 is another critical value. We need to know then where we need to shade. So I'm going to jump to the next slide so we can determine where we should shade, and then I'll go back. We add our intervals between -infinity and 2, between 2 and 5, and between 5 and infinity. When I substitute 0 in my first interval, I end up with a -5/4. When I substitute 3 in between my interval between 2 and 5, I end up with a positive value. And between 5 and infinity, I plug in 6, and I end up with a negative value. Remember, we're looking for x values that are less than or equal to 1. So there are a couple that we're aware of here. I'm going to have our interval between -infinity and 2, and the interval that is inclusive for 5. We have to exclude 2. We have to exclude 2 because x is not defined at 2. Even though our statement is less than or equal to, x is not defined at 2 because if we plug the 2 into the denominator, we would end up with a 0. So I'm excluding 2, although in that interval we certainly are negative. But we can include 5 because 5 is a critical value only when we solved. Going to the previous page then, where we need to shade. We need to shade in the interval again between -infinity and 2. We are negative here. And then in the interval between 5 and infinity, we are negative. So this little piece here, if we were to continue going forever and ever. This last example, we're still going to set this equal to 0 by subtracting that entire left-hand side, that left-hand rational expression. We're going to bring that over to the left. So I'm going to subtract this and bring it to the left, which will provide me with what we see, the x minus 3 over x plus 4 minus x plus 2 over x minus 5. We have our related function then, and we need to find the critical values. Where is x not defined in our denominator? When I look at my denominators, x cannot be negative 4 for here, and x cannot be 5. So we first have our couple of critical values that we need to be aware of when we're going to go look at our intervals. Now we need to solve for 0. So to solve for 0, I'm going to multiply by the least common denominator so that we can eliminate those fractions. Our least common denominator is x plus 4 and x minus 5. Also refer back to Unit 3 as well. So now I'm going to multiply the left side and the right side by our least common denominator. And when I multiply all of them by the first fraction, I see that my x plus 4s would end up canceling, and I'd be left with x minus 5 times x minus 3. Subtracting. When I multiply x plus 4, x minus 5 with the right-hand side, I see that my x minus 5s would cancel. So I'm left with x plus 4 times x plus 2. And when I multiplied everything on the right, anything times 0 is 0. So easy enough to get rid of. Now I'm going to distribute, and distributing I'll have x squared minus 5x minus 3x to provide me with negative 8x plus 15. Subtract, I'll also have x squared plus 2x plus 4x, which would end up with positive 6x plus 8. I now need to distribute the negative because I'm subtracting all of these pieces. I now have x squared minus 8x plus 15 minus x squared minus 6x minus 8. Combining like terms together, I'll have a total of negative 14x plus 7 equal to 0. Subtract 7 from both sides and divide by negative 14. So x is equal to half. We have our critical values. We have the critical value of negative 4, 5, as well as half that we need to take into consideration. So here's negative 4, here's 5, and half. We have our intervals. In between negative infinity and negative 4, I chose my critical value, my test value of negative 5, giving me a positive. Between negative 4 and half, I chose negative 2, but the sign was negative when I evaluated. Between half and 5, I evaluated 3, which gives me a positive. And between 5 and infinity, I chose 6, which gave me a negative. We're interested in values that are greater than or equal to 0. So we're interested in values which are positive. So these values here are positive. The intervals then with which we are going to worry about are between negative infinity and negative 4, between half and 5, or x such that x is less than negative 4, or x is in between half and 5. Again, we want to make sure that negative 4 and negative 5 are excluded because those are the places with which we would end up with a 0 in our denominator. And because our inequality is greater than or equal to, this piece, the half, is included. Hence why we have parentheses here and here for the excluded values that would give our denominator a 0, but yet our half is the included piece. And this concludes our lesson on 4.6, as we are graphing inequalities for polynomials and for rational equations.